Welcome, curious minds, to another deep dive. Today, we're plunging into a topic that is, well, it's quite literally the invisible guardian of our tech world: failure analysis. We're talking about how the most advanced chips on the planet are kept reliable, and we're going to zoom in on its absolutely vital role within Taiwan's formidable semiconductor protective supply chain. Our mission today is really to give you a shortcut to understanding the incredibly precise, high stakes detective work that goes into making sure products like the chips in your smartphone, your car, or even a supercomputer actually work and keep working. Especially now, right, in this era of advanced packaging and heterogeneous integration, where everything's getting smaller, faster, and way more integrated. Prepare for some truly surprising insights that reveal the hidden layers of trust beneath our digital infrastructure.
Absolutely. And failure analysis, or FA, it's sort of like the CSI of the semiconductor world, as you hinted. It's a systematic technical process. It's used to identify, diagnose, and crucially, solve defects or failures in semiconductor components. And these issues can pop up during manufacturing or maybe during actual use or even during testing. Its primary goals are really critical. First, determining the root cause. Is it a material flaw, a manufacturing hiccup, maybe even a design oversight? Second, it dramatically enhances overall product reliability because you feed that crucial data back to the engineers. And ultimately, well, it significantly reduces costs and risks, things like product recalls or huge yield losses. What's really fascinating here, I think, is how its importance is growing exponentially. We're moving into this world of advanced packaging technologies like chiplet architecture, where you combine these tiny specialized chiplets or things like CoOS and system in package, SIPI, all incredibly complex systems.
Yeah, and when you mention advanced packaging, I just imagine the complexity must explode. We're not talking about one chip on a board anymore, are we? What kind of unique challenges does that multi-chip integration, those really complex interfaces, and frankly, the microscopic sizes introduce?
You're absolutely right. It's a whole different ballgame. Imagine trying to integrate multiple different chips, each doing a different job, all squished together in one tiny package, often stacked in 3D. This leads to very specific, almost microscopic battlegrounds for problems. We're talking about issues like delamination.
Delamination, like
Yeah.
layers peeling apart.
Exactly, where layers literally peel apart like an invisible force is ungluing them. It's a huge problem. Or there's electromigration, EM. This one's kind of a silent killer. The electrical current causes atoms to slowly migrate and damage the microscopic metal interconnects.
Oh, wow.
Yeah, it's like a tiny river eroding its banks over time. And then there's thermal expansion coefficient mismatch, CTE mismatch. This is a huge one in packaging. Different materials you see expand or contract at different rates when they heat up or cool down, and that causes immense stress and can lead to microscopic cracks. Catching these early is absolutely paramount.
That makes perfect sense. The sheer precision needed must be just mind-boggling. So with that crucial understanding of what FA is and why it's so vital, the real intrigue begins. How do they actually do it? How do these tech detectives solve these microscopic mysteries? What are the core techniques involved in this high-tech forensic work?
It really is a comprehensive toolbox, yeah.
Yeah.
Designed to peel back the layers, sometimes quite literally. FA employs a wide variety of physical, chemical, and data analysis techniques, and they often start with what we call non-destructive analysis.
Meaning they try not to break it first.
Exactly. The goal is to conduct an initial inspection without damaging the sample at all. Think of it like a medical scan, but for a chip. Key technologies here include X-ray imaging. This is used to peer right into the internal structures. It helps detect things like tiny solder joint breaks or hidden defects within the package layers. You can't see them from the outside. For instance, in something like TSMC's CoWS packaging, X-ray is absolutely crucial for checking the integrity of those incredibly tiny microbump connections between the stacked chips and the substrate. Then there's scanning acoustic microscopy, or SAM. This uses high-frequency sound waves,
Like an ultrasound.
exactly like an ultrasound for chips. It detects internal defects like delamination, those pesky peeling layers we mentioned, or tiny bubbles or voids. It's especially good for looking at the interfaces between different package materials. And we also use infrared thermography. This identifies hot spots on the chip.
Ah, to see where it's overheating.
Precisely. It detects electrical shorts or overheating issues. It basically shows you where the chip is running a fever.
So they're using these advanced imaging and sound techniques to find problems without even touching the chips sometimes. That's pretty incredible. But what happens when those methods just aren't enough? When they have to get a closer look by, well, taking it apart?
Right. Sometimes you just have to go deeper. That's where destructive analysis comes in. Its purpose is to carefully deconstruct the sample for a much deeper physical or chemical analysis of the failure. This includes techniques like cross-sectioning. Here, they meticulously cut the sample.
Like slicing it open.
Exactly. And then observe its internal structures under a powerful microscope. They check for things like delamination or cracks inside. Imagine slicing a perfectly layered cake just to see if there are any air bubbles or cracks hidden inside. It's kind of like that, but much more precise.
Yeah.
Then there's chemical etching. This is used to precisely remove specific material layers.
Like chemical sandpaper.
That's a good way to put it. Yeah, almost like chemical sandpaper, to expose underlying defects layer by layer. And then there's the incredibly precise focused ion beam, or FIB. Now, this is where the detective work gets really surgical, down on a nanoscale. FIB allows for highly accurate cutting and milling, almost like sculpting at the atomic level. And it's often combined with scanning electron microscopy, SEM, which gives you these ultra-high-resolution images.
Wow.
A really compelling example is using FIB-SEM to detect those electromigration issues we talked about in chiplet packaging. You can actually analyze the metal line corrosion or breaks, literally see the damage, atom by atom.
So they can basically dissect it virtually or physically slice it down to the atomic level.
That's amazing. But okay, it's not just about tiny wires and physical integrity, right? What about the electrical performance? What if the problem isn't physical damage, but something wrong with the flow of electrons? You've hit on a crucial point there. Beyond the physical side, there's the equally vital electrical side, and that's addressed by electrical testing. The purpose here is to pinpoint the cause of any circuit functional failures. What's making it not work electrically? This involves things like current voltage, IV testing. This checks for shorts, open circuits, or leakage within the components.
So is the power flowing correctly, or is it like escaping somewhere?
Exactly. Is it going where it should or leaking out where it shouldn't? Yeah. Then there's time domain reflectometry, or TDR. Think of TDR like an echo sounder, but for electrical signals. It sends a pulse down the signal path and listens for reflections or, strange bounces.
Okay.
And those reflections tell them exactly where the signal path might be damaged or blocked because of something called an impedance anomaly. And then there's these really advanced fault localization techniques, things like emission microscopy, known as EMIR, or optical beam-induced resistance change, OBRCH.
Oh, those sound complex.
They are remarkable tools. They can pinpoint the exact physical location of an electrical failure by detecting tiny light emissions or resistance changes coming from the faulty area itself.
You can see the failure electrically.
In a sense, yes. You see the light it gives off or the change in resistance. For instance, in complex CP packaging, these techniques can precisely identify signal interference problems between multiple chips that are all integrated into that single system.
That's fascinating, finding electrical problems by literally seeing light or resistance changes. But chips aren't just electrical components, right? They're also subjected to real-world stresses, heat, physical forces. How do they account for that in failure analysis?
Absolute critical point. That's covered by thermal and mechanical stress analysis. The purpose here is really to evaluate the risk of failure caused by thermal stress or mechanical stress on the components. Key technologies include thermal stress simulation. This often uses something called finite element analysis, or FEA. It's a powerful computer modeling tool. It lets engineers basically stress test a chip and its packaging virtually.
Before they even build it.
Exactly. Simulating how heat spreads, where physical stress points might develop under high temperatures or during thermal cycles, all before you make a physical prototype. Saves a lot of time and money. Then there's thermal expansion coefficient, or CTE, measurement. This is critical. It ensures that the different materials used in a package expand and contract at matching rates.
The CTE mismatch problem again.
Precisely. If they don't match, you get internal stress, leading to delamination or cracking. So you have to measure and match them carefully. And dynamic mechanical analysis, DMA, that tests the actual mechanical properties of the packaging materials themselves, like their stiffness or toughness, how they hold up under force. An intriguing application case here is ensuring the long-term stability of biomedical packaging. Think about chips that might literally operate inside the human body.
Right, that reliability has to be absolute.
Absolutely. You can imagine how vital that analysis would be.
Okay, it sounds like an incredible amount of really intricate data is being collected from all these different analyses, physical, electrical, thermal, mechanical. Are they leveraging AI for this kind of analysis now to maybe speed things up or find subtle patterns that humans might miss?
Yes, definitely. That's a huge trend. We're seeing a significant shift towards data-driven and AI-assisted analysis. The purpose here is to dramatically enhance the efficiency and, importantly, the predictive capability of failure analysis by harnessing big data and AI. One key technology is AI visual inspection. This uses machine learning to identify defect patterns in those microscopic images much faster than the human eye can. A great example is TSMC's application of AI visual inspection. They use it for quickly screening tiny solder joint defects in chiplet packaging.
And that helps how?
Well, it slashes the analysis time from potentially hours down to just minutes. Huge efficiency gain. There's also failure mode and effects analysis, or FMEA. This is a systematic way engineers use to predict potential failure risks before they happen. And this process is now heavily optimized with historical failure data and predictive AI models. It gets smarter over time. And finally, there's the integration of Mazeta data. That means linking the manufacturing execution systems, the factory floor data, with electronic design automation and the chip design data.
Connecting design and manufacturing data.
Exactly. This enables real-time failure prediction and allows for immediate feedback directly into the manufacturing process, making the whole thing smarter and more adaptive. And what's truly fascinating here, I think, is how all these cutting-edge technical capabilities, well, they aren't just about fixing broken chips one by one. They tie directly into Taiwan's strategic position in the semiconductor world, really strengthening what's known as their protective supply chain.
Ah, the protective supply chain. Let's unpack that. How does FA support that specifically?
Well, firstly, FA significantly contributes by supporting advanced packaging reliability at a really foundational level. In complex chiplet and heterogeneous integration setups, FA is what ensures the reliability of those incredibly intricate interconnections, their potential failure points. For instance, TSMC's CoWoS technology, which is a key competitive advantage for them, driving things like AI accelerators. That heavily relies on precise X-ray and scanning acoustic microscopy to detect tiny microbump or substrate defects in their 2.5D and 3D packaging. You have to find those. But it's not just the chip makers like TSMC. They're local equipment providers like Man's Automation. Their stock code is MAIN5443. They supply incredibly high-precision metrology and inspection equipment. These tools are crucial for maintaining clean FA processes, which dramatically reduces contamination risks during analysis.
So the tool makers are key too.
Absolutely. And these companies are evolving. They're moving from just being suppliers to becoming solution co-creators. They integrate their equipment with sophisticated software and data platforms to provide complete FA solutions.
Okay, so it's not just about Taiwan making the chips that power everything, but also about Taiwan making the hyper-sophisticated tools and software that ensure those chips work reliably. And that sounds like it reduces reliance on others, a sort of silent but powerful form of self-sufficiency building up.
Precisely. You've nailed it.
Yeah.
FA critically strengthens local supply chain autonomy. The field of failure analysis, it demands incredibly high precision equipment and specialized materials. And this is where local Taiwanese companies like TestRite, APS, and Advanpak come into the picture. They are actively developing their own FA and measurement equipment. And by doing that, they significantly reduce the industry's dependence on major international players, companies like KLA or Thermo Fisher.
Building that capability locally.
Exactly.
Yeah.
Furthermore, you have local key material suppliers like Changchun and Topco. They play an indirect but really vital role. They provide the high-quality packaging materials needed. And better materials mean fewer initial problems, right?
Yeah.
So it helps proactively reduce common issues like delamination or that CTE mismatch we discussed, which in turn improves the overall efficiency of failure analysis because you're preventing some issues before they even arise.
They're building resilience right from the ground up. That makes perfect sense. Building on that point then, how is this entire field of failure analysis evolving with the sort of broader trends we hear about smart manufacturing data platforms? Is FA becoming part of that much bigger interconnected digital ecosystem?
Absolutely, it has to. FA is actively promoting smart manufacturing and platform development. It's shifting away from being just a traditional, maybe isolated laboratory function. Now it's becoming a much more data-driven and platform-based approach. By deeply integrating those manufacturing execution systems, MES, with electronic design automation, EDA, Taiwanese companies can seamlessly connect data, all the way from the initial wafer processing through to final packaging.
So a complete data thread. A complete thread, exactly. And this allows for real-time failure prediction and, crucially, proactive adjustments on the factory floor. The application of AI, like that AI visual inspection example, positions Taiwan to potentially develop something really interesting. What could be described as an AWS-like failure analysis platform.
Like cloud-based FA.
Pretty much. Imagine global subscription-based services, SaaS, software as a service. Companies anywhere could upload their failure data and get immediate AI-driven insights. This would upgrade those traditional third-party FA service providers into these advanced reliability AI assistant platforms, making cutting-edge FA accessible to a much broader market, including smaller players.
Wow, that's potentially a huge strategic play for them. And what about the global stage? Is Taiwan just keeping this specialized knowledge sort of locked up, or are they collaborating and sharing their expertise to further their global influence? No, they're very active globally. There's significant international cooperation and solution export. Taiwanese companies routinely collaborate with major international firms, think Hitachi High-Tech, KLA, others. They work together to establish shared databases, joint development centers. This collaboration significantly enhances Taiwan's global influence in FA technology, helping to shape industry standards.
So they're helping set the rules of the game.
In many ways, yes. And looking ahead, Taiwan is really poised to become an exporter of integrated solutions, think engineering services plus equipment module packages. They could leverage their leading FA technology to attract international clients who need that deep reliability expertise. It's a testament to their leadership. They're not just building the chips, they're building the trust in the chips and sharing that capability with the world.
That's a powerful position. Okay, so looking forward then, what does this all mean for the future? As technology keeps pushing boundaries, shrinking things down, making them more complex, what challenges are on the horizon for failure analysis itself? And what exciting new possibilities might emerge from this evolution?
Yeah, the future of FA faces several key challenges, but also, as you say, incredible opportunities. On the technical front, a big one is achieving nanometer-scale precision. As chip features shrink below, say, 3 nanometers, FA equipment will need even higher resolution and sensitivity. We're pushing the very limits of physics here.
Harder and harder to see the problems.
Exactly. There's also the pressing need for multidimensional data integration. Analyzing these complex heterogeneous packages requires seamlessly combining electrical, thermal, and mechanical data from different tools into one coherent picture. That's a huge software and platform challenge.
Getting all the data to talk to each other.
Precisely. And for AI, the challenge is constantly optimizing the AI algorithms. This will demand even larger scales of high-quality training data and more sophisticated models to keep up with the exponential increase in chip complexity. The AI has to learn faster. Then, in terms of business model innovation, we'll likely see that significant shift towards FA services adopting the SaaS model we talked about.
The AWS for FA idea.
Right. Cloud-based failure analysis, subscription services, it makes sense. And Taiwan can really leverage this platformization of FA technology. They can use it to attract small and medium-sized semiconductor enterprises globally, companies that can't afford their own state-of-the-art FA labs. This could expand Taiwan's market influence far beyond its borders. And finally, there's the dynamic of global competition and cooperation. It's both. Taiwan will continuously need to compete with the international giants in FA equipment and technology. That's a given. But simultaneously, it's crucial for them to deepen cooperation, to help establish standardized failure analysis processes across the industry. The ultimate goal, really, is for Taiwan to become a global leader, maybe the global leader, in semiconductor reliability solutions through technology export, essentially becoming the world's go-to for ensuring everything, from your phone to your car's critical systems, works flawlessly every time.
It's truly incredible when you step back and think about how this highly specialized field, almost a detective story for semiconductors, like you said, is so absolutely fundamental. Fundamental to everything from your smartphone to advanced AI, even biomedical devices implanted in people. It really is the invisible guardian of our tech world, silently ensuring that these complex, interconnected systems we rely on every single day actually do what they're supposed to.
Exactly. And if we connect this to the bigger picture, maybe for you listening, consider how Taiwan's quiet leadership in failure analysis isn't just about fixing broken chips after the fact. It's really about building trust. It's about ensuring the absolute reliability of our entire digital infrastructure. And ultimately, it's about defining the very limits of what's possible in the next generation of electronics. It's about the peace of mind, knowing that your autonomous car will stop when it needs to, or that your medical device will function perfectly when it matters most. So maybe think about this. What stands out to you about how this foundational reliability, often hidden deep inside the technology, actually ensures our digital future?